Hello, everyone. Like Roy said, my name's Nick. I have a company called Infrasonic Audio. I do consulting for software development of synthesizers, mainly embedded and hardware products, and I'm working on a few products of my own, um, as well as I designed an engine for one of the simple boards called Audrey 2, which is like a feedback synth, which uses actually a lot of the techniques that we're going to talk about today at its heart. So without further ado, today we're going to talk about car plus strong synthesis, which is a quite old by modern standards technique for a subset of synthesis called physical modeling, which seeks to emulate not necessarily, if you think about a subtractive synthesizer, we start with a wave shape, a triangle, a sawtooth, a sine, whatever, put it through a filter. That's a very, mathematically pure oscillation. Physical modeling actually uses physics to attempt to emulate the vibration mechanisms of real world objects and systems. So rather than starting from, a pure waveform, we're actually starting from the physics of a physical object and trying to emulate how that works. Now, car plus strong synthesis is actually a very, 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 very simplified way of doing this for a string, like plucking a string, like on a guitar or any other plucked instrument. Dates all the way back to 1983, and the paper was released in
Should
Computer
I
Music
share
Journal.
your screen now?
Yeah. Let's share this screen. We'll take a look at some stuff, and then we'll listen to a sound example, and then I'll talk about where we're going to go from there.
Okay, let's do it.
Great. Yeah, so this paper, all the way back from 1983 in the Computer Music Journal, Kevin Karplus and Alex Strong, which are the namesake of this algorithm, Karplus Strong, released this paper about plucked string and drum timbres. And they had a really just simple and pretty ingenious way of emulating the sound of a plucked string. So we can actually, let's just take a quick listen to what that sounds like. Now, this is not the original algorithm, but it is a sample from 1989 after a couple other famous physical modeling guys got their hands on it and did some interesting extensions to it. So this is a Bach fugue recorded in 1989, and this was actually used in an Apple I think WWDC. No, it was the next computer launch. Steve Jobs actually played this, and they had a live orchestra or live string instruments over it as well. But this is just a synthesized version. So let's take a listen. Hear that? I hope that worked. But
Actually,
that
we are. Oh yeah, okay, sounds good here.
sounds good.
But
Okay,
yeah, okay.
great. So yeah, that was a Bach fugue arranged on a DSP from the Next computers in 1989. And so it sounds like a computer, but it's a very interesting sound. You wouldn't necessarily hear that sound from a subtractive synth. It's a totally different technique. We're not using waveforms or oscillators and filters. We're actually just using noise and delay. So I'm going to dive into how this works. Roy's going to help moderate with any questions that people have from the chat. Please feel free to ask, and he will interrupt, and we can kind of dive deeper. But I'm going to start in BCV Rack with the simplest possible, at least as far as I can tell, implementation. And then we'll look at a little bit of code for the Daisy and Arduino with the simple fix board. And then if we, depending on where we land on time, we can talk about some more advanced things you can do with this technique and more advanced examples all the way to the mutable instruments code. If you've ever heard the plucked string mode on rings or even plats as basically the same code, that's car plus strong. That's the same algorithm with a lot of additional DSP extensions to address some of the shortcomings and make it sound more interesting, more realistic, or unrealistic, because that's one of the interesting things you can do with physical modeling as well, is simulate physical systems that would be very difficult to recreate with real objects. So here we are in VCV Rack. Now, what you can't see, I have a keyboard on my desk. I've got a key step on my desk, so I'll be playing notes as we talk, and hopefully that's coming through. But yeah, so we've got a patch here in VCV Rack. Just to kind of step through how this works at a high level, we're getting volt per octave information from the keyboard, from the key step 32, and we're getting gate information from the keyboard. And what we're doing is taking some white noise through a VCA. We're taking the gates from the keyboard and using this gates module to give them a fixed length of about 5 milliseconds. So it doesn't matter how long I hold the key, the gate comes in and then the gate comes out as a short noise burst. And we can actually hear what that sounds like. Just this short little burst of noise. And we're taking that little burst of noise and we're feeding that into this waveguide delay module. Really what we want is a delay line. So we want to take the samples and delay them by a certain amount of time and have access to the output of that delay. The tricky thing about doing this in VCV Rack and why I'm using this specific waveguide delay module from SkyTam, I'm not sure how to pronounce the creator, versus the the fundamental VCV delay, is that the fundamental VCV delay is designed to sound good, right? It's designed so that you can put stuff in it and it sounds good, right? Like a nice delay, like you might have in a stomp pedal or a plugin or something like that. And to make it sound good, it actually applies a little bit of modulations. It adds some color to it. I think you can get it to sound pretty clean and pretty pass through, but to get exact delays, which we need for this algorithm, that's what this module is meant to do. So we can actually send the volt per octave to the delay amount. And what that does is it sets the length of the delay line to exactly one period of the note that we're trying to get out. And that's in essence how this algorithm works. So before, going any further, I'd like to just demonstrate what happens if you put at a very, very low pitch. So a pretty long delay time. If we put just a little burst of noise and we have a high feedback amount. So this is the feedback amount. If we do this, so that's a fairly long delay. We just get this little burst and then it echoes over and over and over repeatedly. So that's got a period that's sort of sub audio. It's a very, very low frequency. But if we go up octaves, we can start to hear that turns into a tone. It sounds like a note. So this is the length of the delay line being equal to one period of the note that we're trying to hear, the fundamental of the pitch that we're perceiving. And this is with just a really short little gate, or a gate of noise. So just a little pluck. So that's sometimes called a resonant delay line. That high feedback level enables it to kind of keep feeding back through the delay line and repeating itself. I'm actually going to change this for a moment so that we're hearing just the pure feedback with no other filtering or alteration on it. So that's the pure feedback. So it'll go for basically forever because this is a very, very high amount of feedback. This knob controls the amount of feedback feeding back into the delay line. So you can kind of just start to maybe make those connections that if we put a very, very short burst of noise into this delay line and we feed it back, and the length of the delay line is one period of a pitch that we can perceive in the audible spectrum, and then we feed it back on itself over and over and over again, it sounds like a pitched sound. Doesn't sound really like a string, but it does sound like a pitched sound, right? So to actually make it sound like a string, we have to do a couple other things to it. Before we do that, I have to demonstrate this because it makes me laugh. If you've ever seen Futurama, the cartoon Futurama, you may be familiar with Hypnotoad. It's this hypnotic toad TV show that makes this really crazy sound. We can actually make that sound with this patch if we put like continuous noise. So I'm going to make the gate really long. So we're putting continuous noise through here at a very low pitch. Oh, too low. So there's Hypnotoad.
That's cool.
There we go. That's Hypnotoad.
Yeah.
So that should be a familiar sound if you've ever seen Futurama. But sorry about that if that was loud. I was trying to manage it. But that's the idea. So we're just taking a delay line, one period long of whatever note we're trying to achieve. We're putting some noise through it, and then we're feeding it back on itself. The amount of feedback controls the decay time. So very long decay time. And if we turn this down, we get a shorter decay time. Something that will be important maybe a little later is that if you think about every time it goes through the delay line, it attenuates a little bit. So it gets a little bit quieter every time it goes through. Well, depending on how long that delay line is, that's actually going to influence how long the note is. So lower notes at the same feedback level are longer than higher notes. So there's same note, just higher octave. It gets shorter as you go up, even though we're not changing the feedback time. That's because it's going through the delay line much quicker, so it's attenuating a lot faster. Cool. Yeah, I'm just going to keep going unless there are any questions from Roy or the chat, but please feel free to interrupt, Roy, if there are.
No, it's pretty good for now. I
Okay.
do see now. Keep it loud. Too quiet on stream. Noise.
Okay. Sounds good. Thanks for the
I don't
feedback,
think we have
Ray.
any noise suppression, Ray, but we'll try. I can actually. Is this better in terms of volume? Let's also bring Nick a bit higher. Can you guys let us know if this is now sounding better?
Let's assume it is. Seems it's definitely louder for me, so I assume it's louder in the stream too. Cool, we got a thumbs up. Great. So yeah, so what we've covered so far is, we're just taking some noise and we're putting it through, just a very short gate into the VCA so that we're just sending a quick little burst of noise through this delay line. And the delay time is proportional to the volt per octave information, which sets it to the length of one period of the note we're trying to hear. And then we're feeding that back on itself with a high amount of feedback. And that gives us this resonant tone. Now, it still doesn't really sound much like a string, right? It's kind of, maybe, but it's really just kind of a buzzy sound. So to actually make this sound like a string, the trick to the Karplus-Strong algorithm, what they came up with was to put a low pass filter here in the feedback loop of the delay line. So you can kind of see that in this diagram. If we think about how a guitar or any plucked string instrument works, intuitively, this kind of makes sense, right? Because the higher frequencies tend to dampen out a lot faster than the lower frequencies. So that's essentially what that low pass filter is doing. As the structure of the string, the tones that resonate in that delay line continue to feed back, the higher frequencies are attenuated faster than the lower frequencies if we put a low pass filter in the feedback loop. So the low pass filter in the original algorithm is extremely simple. It looks like this. So it's really just a 2-sample moving average. So it's the current sample plus the z-1 means the previous sample. So it's saving a sample from the previous iteration. And it's taking the average of those. It's multiplying both of those by 1/2 and summing them. And when you take the average of 2 samples or more, it's a 1-0 filter. Technically, that's having a low pass effect, a very gentle low pass effect. And the way we can do that in VCV Rack, here I've got a module that adds 1 sample delay. So I've got the output here from the waveguide delay going through this module. This adds 1 sample of delay, which is sort of the lower path here. That's the previous sample. We're getting, one sample behind where we are now. And then we're taking the current output and I just put these both into a crossfade, and I've got the crossfade right in the middle. So it's taking sort of both of those summed together at equal weight. What it's not doing is dividing by half, because I think the crossfade has a different curve than that, but it's close enough for what we can demonstrate. And then finally, what this is a DC blocking filter, because what can happen when you put a noise burst in, if that noise burst has any DC offset, that can build up over time and actually sort of squash out the note. It just doesn't sound very good in certain settings. So we want to block that DC, that static offset from the feedback loop, so that we're only we have no offset in our feedback loop. And when we do that, it starts to sound a lot more like a string. So this is basically the original Karplus-Strong algorithm with no extensions. And we can hear the difference by turning this off. So now I'm just taking straight out of the delay line and back in, no filtering. And if we add the filtering, then it sounds more like a plucked string. So this, in essence, is the way I was able to achieve the original, very simple Karplus-Strong algorithm in VCV Rack. And I can make this patch available in some of the materials, I think, that will be shared afterwards. It does use a couple of third-party modules, which I can list in the notes as well. But in case you want to play with this, great. Take a stop here for a moment. I'd like to talk a little bit about tuning as well on this algorithm, because that's an important concept. But before we move on, any questions in the chat? Anything that I could go over more clearly from Roey or from anybody in the chat?
Yeah, thanks, Nick. I think, first of all, this is very cool. This is actually the first time that I'm seeing how a filter is working in the digital domain. So this was really insightful, and I had no idea, I should have expected, but I had no idea that VCV would also offer these kind of modules, and people actually create a module that is just delaying in one sample. If anyone has any questions about this process, feel free to share now. To me, this was really new. Why didn't you just use a regular filter, like any filter on VCV?
That's a really great question, and something we're actually going to get into, and it has to do with tuning. Yes, you can use any filter, and in fact, sometimes it sounds a lot more interesting or better if you use a different type of low-pass filter, but tuning becomes an issue. Essentially, this filter is really simple. It's just average of 2 samples, and like you mentioned, you can do these things in VCV Rack. It's maybe you have to think a little bit differently about it than if you were doing this in, say, a computer music environment like Pure Data, Maximus P, Super Collider, one of those environments. Then you kind of generally have access to those lower level surgical tool abstractions. We have an exact perfect delay line. We can do a 1 sample delay. We can do an arbitrary multiplication. There are, of course, other modules in VCV Rack that allow you to do certain things like that, but it's a little bit of a different way of thinking about it than, at surface level, VCV Rack being a Eurorack emulation system. It would be very unlikely to find a Eurorack module that is a 1 sample delay. In fact, that would be almost impossible. So to think about it, the digital domain, the digital kind of back end of VCV Rack, and to put it together this way was actually kind of a fun challenge. But yeah, so that's kind of what we ended up with. Now, to address your question about why not use another filter, I actually have another VCV patch I'm going to come back to a little later once we kind of switch over to DAISY and keep things in this simple original algorithm topic for a little bit longer. But to kind of think about the effects of a filter on the delay line and why that's important, I'm actually going to point out one feature of this waveguide delay, which is actually pretty smart, is this delay adjustment. So this Basically, in VCV Rack, every time you go through a module, for the most part, some modules have additional buffering, but at minimum, each module is adding one sample of delay already. It doesn't matter what it's doing. It could just be passing the signal through. That's just how VCV Rack works. At minimum, each module is adding a sample of delay. So you can see I've got 3 modules in my feedback loop here. And I have this delay adjustment. I don't know if that's going to be legible, but this delay adjustment is set to -4. And the reason it's set to -4 is that
Maybe you could you maybe zoom in? Just
you
like,
can't zoom in on the tooltips, unfortunately. So I
okay.
can zoom in on the control, but the tooltip text you're not going to be able to read, I don't think, unfortunately.
Okay. But yeah, but that's already much better. Yeah.
Okay. Yeah. So this delay adjust is set to -4. And the reason that it's 4 and not 3, I've got 3 modules in my feedback loop, is because even the waveguide delay itself, if I were to feed this output directly back into the feedback input, which I can, and that works just fine, even that itself is adding one sample of delay because it has to process the output. And then on the next tick, the next sample that it processes, it gets that output back into the feedback. So even that itself is adding one sample of delay. So to use this with proper tuning, all those notes are in tune, you need to set this delay adjustment to minus, you can only set it to negative numbers, but the number of modules you have in your feedback loop plus 1 for the module itself. So I've got 4 minus 4. If I don't set it to that, let's say I set it to, and it's fractional, by the way, so you can set this to, it doesn't have to be an integer. Let's say I set it to -2. Now you can hear it's out of tune, right? As we go up, it starts to get flat. That's because this additional delay is actually extending the actual net delay through the feedback loop by 1 sample per module, and this compensates for that. The other interesting thing about this is that if you think about delay in units of samples, if we have a low pitch, so we've got a note down here, say something like this, this has almost no effect. If I change the delay adjustment, it doesn't sound like it's going in and out of tune at all. That's because relative to the length of the period of that low note, the length of the period is pretty long. One sample isn't really changing that very much. As we go up in pitch, the period of our delay line, or the length of the delay line and the period of the fundamental of the note, becomes smaller and smaller. And one sample offset can actually result in a pretty big effect on the pitch. So if we go up, you can actually hear that changing as I turn it. So as you go up in the scale, the tuning tends to become more sensitive to how inaccurate your overall feedback time is. This is actually really important for the original algorithm because at the time in 1983, when Karplus and Strong developed this algorithm, they were using delay lines with exact sample lengths. They were not interpolating between samples in the delay line to achieve, an arbitrary length of time. So if one period of your desired pitch actually falls between 2 samples, so the time length of one period of your pitch doesn't fit neatly into exact samples, then it's going to be out of tune. And as I just demonstrated, for the lower notes, it doesn't really matter that much. It's just a little tiny bit out of tune, a little bit tiny off from the target period. But for high notes, it starts to go more and more out of tune. And this is actually one of the what's the right word? Inaccuracies, I suppose. One of the drawbacks of the original algorithm is that they were using non-interpolated delay lines. So as you go up in pitch, you're limited to exact sample lengths in your delay line. The higher notes become more and more out of tune. This waveguide delay module, of course, is not doing that. This is using an interpolated delay line with a really high quality interpolation between samples. So it has essentially no effect on the tuning. To go back to your question about why not use arbitrary filters, well, a 1-0 filter, this moving average of 2 samples, is has what's called a linear phase response. So it doesn't matter what frequency you're looking at, they're all delayed by the same amount of time. That's a simplified way of thinking about it. Not all filters are like that. In particular, infinite impulse response filters, which are pretty much all of the, most of the popular synthesizer digital filters and emulations thereof, are infinite impulse response filters, which actually have non-linear phase responses, and in particular around the cutoff, it's the delay is frequency dependent. So the delay of each frequency going through the filter is different depending on what the settings of the filter are and what frequency you're looking at. So what happens there, and we'll see that when I come back to the other VCV patch, if you put an arbitrary filter in there, depending on how your filter is set and what pitch you're playing, the tuning can be all over the place. There are ways to compensate for this. Modern implementations, including the rings code for mutable instruments, compensates for this because you can actually derive mathematically the phase delay, or sort of the average phase delay around your cutoff or whatever filter settings you have, and then compensate your delay time to accommodate that so that things don't go out of tune. So yeah, that's kind of why not use an arbitrary filter. Yes, you can absolutely, but you may run into tuning issues. If you're writing code to do this, you can accommodate all that. If you're doing that in VCV Rack, it's a little bit harder. It's at best, it's going to be guesswork, just sort of like adjusting the delay based on the volt per octave information to try to accommodate, what the filter's doing. But it's a lot of sort of guesswork and guessing and checking. And we'll take a look at that a little bit later.
And would you, like, if you want to shape the sound further, it would make sense for me to just add a filter right after it. That would work, right?
Right. I'm sorry. Right. Add the filtering right after what specifically?
So you have now that filter that makes it a bit more like it sounds more like a string, and then you would add another filter after this to shape the sound a bit more.
Actually, we can replace this filter with any arbitrary low pass filter and get a similar effect. But we will run into tuning issues if the filter does not have a linear phase response. If we put the filter on the output,
Yeah.
then you're just going to be sort of rolling off the frequency of the entire sound. It's not the filter. If the filter is not in the feedback loop, it's not affecting the samples over and over as they go through the feedback. That's what's getting this string-like sound, because every time the sound goes through the feedback loop, it's filtering it again and again and again. It's a very gentle filter, so the effect is not like super pronounced, but that's the effect it's having on the sound.
And can you actually make the effect more pronounced if you would not work with one sample but two samples or three samples?
Sure, absolutely. Yeah, if we made this a longer, there's so many different filters you could use here, and we could use a longer running average filter that would change the low pass response. This just happens to be like the simplest thing. This is what the original algorithm was using, this two sample 1-0 filter. And I think I saw somebody in the chat ask to go through this again. So essentially what's happening here is we've got the output going to three places. So here, this is just the output that we're listening to. So this bottom patch cable here is going into the spectrum analyzer and just out to the audio interface. So that's actually what we're listening to. The output is also going first to one input of a crossfader, and then to a single sample delay. So this is just delaying that by one sample and into the other output of the input of the crossfader. And we have the crossfader in the middle, so it's giving equal weight to these two signals. And what that's doing, much like we see in this diagram, so this would be like the direct output into one input of the crossfader. This Z-1 is a one sample delay, so that's the one sample delay. And we're summing those together, and we're multiplying by 1/2 in this case, in this diagram. We're not doing that here. We're kind of compensating for that by lowering the feedback amount, but the effect is the same. So And the last thing here is just the DC blocker. That's not really important for the filter. That's important to avoid DC building up in the feedback line. But that's kind of what we're doing. We're just taking the average of the current sample and the sample that we last output. So one sample before that. And by taking the average of these two, it's a very gentle low pass response. So any like fast changes in the signal will be filtered out very, very gently.
Yeah, and maybe you could also talk a little bit more about the SD module. Is this simply just a utility that allows you to take like to delay a sample? Just
Yes,
one
that's right.
sample?
Sample delay. So this is from Grande, and this is just, input. You've got 3 of the same section repeated, input, and then 1 sample delayed and 2 sample delayed. So this is just a utility to kind of do this exact thing. There may be other reasons you want to do this for latency compensation, or who knows how you might use it in VCV Rack. I'm sure there's a million ways to use it. But in this case, I'm using it to achieve the filter.
Right. So if you would want to make it more steep, you'd basically need to have 2 or 3 or 4 of them.
Yeah, in that
Changed.
sense, you're basically recreating a digital filter with individual modules, like the actual inner workings of a digital filter. Just
Yeah.
for a moment, I don't want to spend too much time in here yet, but I'm going to skip to my other patch because this shows us. Um, this is a lot more complicated, but the same section here. Just to focus on this for a moment, it's basically doing the same thing, but instead of our single sample, two sample average, I've got the output going through this surge filter, low pass 12 dB filter with 0 resonance. It's not on right now. Let me turn it on. Let me turn that up. Sorry. So that sounds, there's reverb on that too. Let me turn the reverb up. But that sounds even more realistic than what we were hearing before. And this is just as a result of using a different filter. But like I was saying, the phase response of this filter is frequency dependent, and it's also cutoff dependent. So we can actually hear this go out of tune as we reduce the cutoff. Of course, the note gets shorter because we're attenuating the signal in general more as we reduce the cutoff, but it also goes out of tune. And it's going to go out of tune less for lower notes than it does for higher
fantastic.
notes. So that almost sounds like, I don't know, like you're pressing on the bridge or something. Like you can do these types of things with string instruments to like purposely make the notes go out of tune. We may not want to do that intentionally, but hey, it sounds kind of neat. We're going to come back to this later because there's a lot more cool stuff you can do to make a more realistic sound. But I want to kind of wrap up on the simple version first and see if we have any lingering questions here. And then maybe we can look at some code for the Seed and sort of listen to how this sounds, this exact same implementation looks and sounds on an actual Daisy Seed.
Yeah, we pretty much covered the questions. People seem to be very happy with the explanation. I think it's fantastic. This is a lot of new stuff for me as well. So yeah, I guess we can continue. If there are more questions, feel free to ask and I'll bring them up.
Okay, sounds good. So hopefully you guys can see this on the camera. I've got a simple fix board here. So I've got a Daisy Seed on the SynthUX simple fix. I've got 4 potentiometers hooked up to it. And then we just got the mono output going to the mixer. So I'm going to play what this patch sounds like first so you can hear it. So really, we just got a plucked string going up an octave. Every second, we jump up another octave, same note. So I'm not actually using any of the potentiometers in this particular Arduino code example. We're just playing sound through the Seed. So there's no controls. It's just doing the same thing over and over. But essentially, I'm doing exactly the same thing I was doing in VCV Rack, but in code. So for the sake of time, I'm not going to focus too much on the language stuff here. If anybody has questions, please feel free to ask. But this is C++. This is using Daisy Arduino, which is the Arduino support library for the Daisy, um, or Arduino flavored C++, I suppose. But what I've got set up as far as audio objects is I've got a metro just for timing, just to sort of like trigger the note once per second. This is like a metronome object. It just gives you kind of a true state at a particular frequency, so you can use it to sort of time things digitally. And then I've got a delay line. And this delay line syntax, if you're not familiar with C++, may be a little scary, but basically this is saying it's a delay line of floats. So it's just a big array of floats, and it has a certain maximum length, which I defined for a minimum pitch of 20 hertz. So we don't really need a super long delay line for this. That's still fairly short, but we want to make sure it fits in memory. So the lowest note we can play, the longest period, in other words, the longest amount of delay we're going to use is for 20 hertz. And I think the lowest note I'm playing is still a little bit above that anyway. But that's really it. And then I've got some helper variables here. But essentially, how this is working is I mentioned the metro. So every sample in our audio callback, so this is happening 48,000 times a second, we're processing these samples. We see if the metro is giving us a trigger. And if it gives us a trigger, its process call returns a number that's not zero, greater than zero. So if it gives us a trigger, now we want to put a short noise burst through our delay line, just like we did in VSV Rack. At the start of the trigger, we're also going to calculate our string frequency. So in this case, we can't change the string frequency between triggers. We're just updating it every time a trigger happens. In another case, or if you were doing this and you wanted to be able to actually adjust the pitch while the note is ringing out, you might want to put this stuff outside of the trigger loop, just so you're able to constantly change the delay time. But here, basically every time the trigger fires, we're going to update how long we're reading out of our delay line to be equal to one period of the frequency that we're trying to achieve. So the frequency we're trying to achieve is, we've got a base note number. There's a MIDI note number of C1. And then we're adding to that 12 times whatever octave we're on. So if the octave is 0, this just remains 24. If the octave is 1, then we're going up to 36, so on and so forth. That's adding 12 semitones, or 1 octave, every time that octave integer increases. And then we're taking M to F, which is MIDI note number to frequency, and we're getting a frequency in hertz out of this. So that's our frequency in hertz, and we want to make sure that that's above the minimum string frequency. So the minimum string frequency, again, was used to define the max delay time. And this just ensures that, if we, for whatever reason, this produced a frequency that's below that, then we're clamping it so it's at a minimum of our minimum string frequency. Then, and I've got some code commented out here, but I'm doing this the way they did originally in the algorithm, by casting this to an integer. It's technically ends up as a float, but this just sort of floors it out. So if this is a fractional result, if it's a non-integer result, this just sort of takes the next lowest integer as a result. Sample rate divided by frequency. This will give us the time in seconds, samples, the delay length in samples for that frequency at our sample rate. So this is the delay length in samples that we need to process the noise through in order to achieve whatever frequency we're trying to achieve. In exact samples, not in fractional samples. Then we need to put that many samples of noise into the delay line. So we want to fill the delay line up with noise at that exact length. If we put more than that, then you tend to hear noise ring out. We start to approach that hypnotoad sound. If you put less than that, it's fine. You'll just get like a more narrow kind of a pluck sound. But the original algorithm was fill the whole delay line up, however long it's going to be for this pitch, fill the whole thing up with noise. So we're setting a variable to that to tell us how much noise we have to put in. How many more samples of noise do we need to put in this delay line? And then on every trigger, we're just increasing our octave until we reach the maximum, and then this modulo will wrap us back around. So that's why we're hearing, let me reset this here. goes up, and then it wraps back around to the bottom. So yeah, so now at this point, we've sort of set everything up because we got a new trigger, we calculated our frequency, we calculated the length of delay line we need to achieve that frequency, and we calculated how much noise we need to put into this delay line. Now, we have a variable for what's going into the delay line. And if we still have a non-zero number of remaining noise samples, we need to put a random sample into this delay line. So this is just a helper function that takes rand, just the simplest possible C random integer, normalizes it to 0 to 1, and then further normalizes it to -1 to 1, which is sort of the audio range of floating point samples that we're working in. So this gives us a random number, floating point number from -1 to 1. And we add that to our delay line input. So this is what's going to go into the delay line on this sample. We add some noise in, and then we decrement the remaining noise samples. Now, once this reaches 0, we're not going to be adding this noise in anymore. So that'll just be 0 after this runs if we have finished adding noise to our delay line. Now we need to read a sample out of the delay line at whatever delay length is one period of the note we're trying to achieve. So we read it out, store that in another variable. And note that this is using linear interpolation. This is an exact integer of samples. So in this case, it doesn't matter. It's going to read exactly one spot in our delay line array, just one sample exactly out of the array. And then to calculate the output that we're going to actually listen to, this is our moving average filter. So we have our delay line output. That's the sample we just read out of the delay line, plus the last sample we read out of the delay line, which at the beginning of the program is just 0. And then we multiply that by half. So we're averaging these two samples. Then we store the sample we read out of the delay line in our last sample variable so that we can use it on the next iteration of the loop. Finally, to write back into the delay line, we have our delay line input variable, which is noise. If we're still putting noise in, that will contain some noise, plus equals, so we're adding to it the output sample, which is the feedback. So that's the sample we just read to the delay line. And then we take our output sample and just attenuate. That's kind of the whole code for doing this. And I'll make this available as well.
Nick, you were breaking there in the last couple of sentences. Could you repeat that?
Oh, sorry. So where from about the average filter or the feedback?
Yeah, just the last bit. So yeah, you could repeat from the feedback.
Yeah, so the feedback, this delay line input variable will contain noise if we're still processing noise. If we still haven't finished putting noise into this variable, it'll contain some noise, or it'll be nothing if we've already finished putting noise in. And then we're adding to that our output sample, which is the output of the filter. So this is the output of the 2-point moving average filter, which is this. So that's the output of our delay line through the filter. And we're adding that back together and putting that into the delay line at the start. And that's what this write is doing, write delay line in. And then finally, we're just assigning that to the outputs in the audio callback so that we hear it. And the times 0.5 is just so it's not too loud. It's just a little bit of attenuation. And when all is said and done, this is what that sounds like. So that's the code for the basic Karplus-Strong algorithm. And for tuning, if you remember, I was talking about how the original algorithm is using exact integer delay length, which results in inaccurate tuning in the higher octaves. It's actually a little bit hard to hear. The higher the sample rate is, and this is 48 kilohertz, the less effect this will have because our samples are actually smaller in units of time. Back then, they were running at lower sample rates, so this actually made more of an impact. But we can actually see, if we look at this in a tuner, we can actually see that As it goes higher, it gets pretty out of tune. Gets pretty out of tune there on the upper octaves. Not as much as you might think, but it does get a little out of tune.
Not more than my guitar.
Yeah, not more than a guitar, maybe.
Yeah.
But if you want it to be perfect, we can use fractional delay lengths. And so here I'm not casting to an integer. This is a floating point ratio. This may have some decimal values. And the reason I'm subtracting half from this is because the result of our filter actually adds half a sample of latency in this case, because it's a little different from VCV Rec, because VCV Rec has the one sample per module of latency. Here, this filter, this moving average filter here, current output plus last output times 1/2, that's actually effectively adding half a sample of additional delay. In fact, if you know how delay line interpolation works, say you're trying to have a delay amount that falls between two samples in equivalent time in seconds, then the simplest way to do that is linear interpolation. How far are we between these two samples? Let's take two samples and interpolate linearly between them to get an approximation of the value that would fall between those two samples. In this case, it's exactly the same as linear interpolation by half. So we're just equally weighting the two samples. So this is actually an additional half sample of delay in our delay line, which is why we're subtracting here 1/2 a sample to compensate. If I run this, I just want to show that this will be perfectly in tune. Take a minute to compile here.
Michael, and also I have a similar question. Michael's asking, how much does the character of the noise matter for the result? And I would add to this, what elements make a big difference to the sound character in this very basic design that you have there?
Great question. We are getting to all that in our next section, but I'm happy to answer a little bit of it now after we look at the tuning here. So you can see on the tuner now it's actually perfect. The low notes don't quite get picked up, but the high notes are essentially perfectly in tune now, directly in the middle. They don't actually sound quite in tune because of, interestingly, how we perceive plucked strings. There's a thing called stretching, which sort of seeks, as you go up in harmonics, to sort of extend the delay time a little bit to make them sound more in tune. Because as we perceive that, it actually sounds slightly less in tune as we go up. I don't know if you can hear that, but it's an interesting phenomenon. Cool. So excellent questions. How much does the noise character influence the sound, and what other factors influence the sound? The answer is a lot. And in fact, one way we can achieve some really interesting variations in timbre is by changing what we do with the noise, whether it's the type of noise we're using, filtering the noise in certain ways, has actually a pretty big impact on the sound. To think about this sort of from a physics or physical world analogy, the delay line and sort of the feedback filter in the delay line, you can think about that as the resonator piece. So once we have some sound in our system, once we've excited it with some energy, how is it responding over time? We're damping the high frequencies. The harmonics of whatever period of delay we have are building up, because I didn't mention this earlier, but the reason that happens is because of constructive interference. So, we're adding it back on itself. And if the sort of energy, the partials in our spectrum of noise that fit directly into that feedback length actually reinforce each other. So we have one period, let's say there's some energy at, whatever the fundamental is, that is going to build up itself. It's going to reinforce itself as we add it back into that delay line. Same with all of the exact harmonics. So multiples of that period, or divisions of the period, multiples of the frequency, those actually add together constructively. And we can actually demonstrate that pretty interestingly by, let me turn the feedback up here. So if we switch notes, you sort of hear that energy just immediately die and switch to the new note. If we go down in octaves, so you can actually hear the upper octave still in the sound if you listen carefully. You can still hear that upper octave, even though we've changed our delay line length, because that original fundamental is now the second harmonic of the new one, which is an octave less. So that energy is still allowed to constructively build on itself and resonate in that delay line. Whereas if we switch notes, we lose that first note. Even though this isn't a polyphonic patch, it almost sounds polyphonic if we go down an octave. If we go up an octave, we don't have that phenomenon, because the fundamental energy at the lower octave is now that fundamental frequency is too long for a delay line. It doesn't, it's not allowed to build on itself. Let me turn the feedback up. So we don't hear the lower sound anymore. It goes away if we go up an octave. If we go down an octave, we still hear the upper sound, because all those harmonics are still part of the harmonic series of the octave below it. And before I go back to the question, one interesting thing I didn't show as well is you can actually make this feedback have negative feedback, so multiply by -1 before feeding through, and then we get a really interesting sound. It's kind of like a hollow tube. And the result that's having is it's actually only allowing odd harmonics to come in, so it's kind of like a square wave. Sorry for the aside, I just had to demonstrate that because I think it sounds pretty cool.
No, it's fascinating.
Yeah, so going back to the question, what effect does the noise have on the system, and what else can we do to make, interesting things happen in our delay line? So here, I forgot to save my setting. There we go. Here we've got what I showed before, which is the Surge XT filter is now what's in our delay line. So obviously that sounds pretty different from what we were hearing before. It sounds almost a little more realistic, like maybe an acoustic guitar or something like that. But you can hear as we go up, it gets out of tune, and that's because of the nonlinear phase response of the filter. But let's take a look at what we can do to the noise. So here I've got the noise going through 2 more filters before it goes through our gate to stick it in the delay line. I've got these filters off right now. They're not doing anything, but if I mix them in, you can hear it gets a lot fewer higher harmonics in the initial sound. That's because there's less higher frequency energy in our noise burst. We filtered that out. So there's no energy up there, which means those harmonics can't resonate because they weren't seeded with any energy. You can even bring that way down, get a nice soft sound. So this is kind of like how hard you're plucking the string, perhaps. A good analogy for that. And in fact, if you map this to velocity, so if I take the velocity here and modulate our frequency with velocity, then you can hear as I play the note harder, we can get more energy in it. So the velocity now becomes analogous to the pluck stiffness or the pluck velocity, how hard we're plucking the string. So this is all what I was getting at earlier. This is all, again, sort of analogous to the excitation of the signal, where the waveguide delay, the feedback delay line, and the filter that's in that delay line is the resonator. So that's like what it's doing with the sound over time, how the steady state system is working. But how are we getting energy into that system is more like, that's what's called the exciter or the excitation. A noise burst is the simplest possible thing, perhaps. If we filter that noise burst, we're sort of changing the character of the excitation. So filtering is one thing we can do to do that, and that has a really interesting impact on the sound. We can also use an envelope instead of a gate. So here you can see now this is envelopes. That's what this scope is showing here. Let me zoom in a little bit. And if we change the decay, if we increase the decay of the envelope, so now this envelope is affecting the amplitude of the noise that we're putting through. It's almost like bowing a little bit, something like that. We can also increase the attack time. So that's kind of like a bowed sound. Which is pretty interesting, right?
That's
I love this
fantastic.
stuff.
I mean, the last two bits were absolutely like, oh my god.
I love this stuff. This is my favorite part of
Yeah.
this one.
Hold on before,
Yeah.
before you continue, because there are some people who are a bit still confused about how you actually got it tuned. Maybe you could repeat that bit.
How the tuning is working from the keyboard information? Is that the
Yeah, like
question?
how do you, like, what is the difference? Maybe people came a bit later. What is the difference between using a regular filter and that very specific filter of like one sample? How do you make sure that you're actually getting carpal strong that is tuned?
Right. So the very simple filter of one sample, that is a finite impulse response filter. It has a linear phase response. This is getting a little into digital filter theory, which maybe is a little out of scope for this talk. But that one sample averaging filter, two sample averaging filter, it's what's called a 1-0 filter. It has a 1-0 in its zeros and poles projection, and it has a linear phase response. It's not doing anything to the phase on a frequency dependent basis. So it has a constant delay of like a half a sample, because we're sort of interpolating between the previous and the current sample in that filter. So the overall group delay of that filter is half a sample, and that's what we're accommodating for when we use that filter. If we use a different type of filter, it may have a completely different phase response characteristic. It may have different overall group delay, and it may have nonlinear phase response in general, which means that different frequencies will be delayed different amounts. And in some cases, we can use that to our advantage to do crazy things to the sound. That's actually one thing Rings does. I know that's maybe not the best explanation, but it's a little difficult to explain without really understanding digital filter theory. And I wasn't planning on talking too much about that in this talk. So suffice to say that the tuning is dependent on the overall phase response of whatever, and additional delay of whatever you have in your feedback loop.
Great. So there's a follow-up question here. How does 1 volt to 2 volt from CV translate to octaves and the delay frequency time?
That's a great question. Yeah, so I've got the volt per octave signal from the keyboard coming here. You could ignore the attenuator for now. So this red cable is coming into the delay input of the waveguide delay. And the waveguide delay is implemented in such a way that it's taking into account volt per octave. It's doing the math to convert your volt per octave into the correct delay time for the pitch that you're going for. And you have an additional offset here. This pitch just, so you can kind of tune it with whatever sort of offset you want to that. By default, it's just a C. It expects 0 volts as C, which is kind of the standard. But say we go from 1 volt to 2 volts, that's up 1 octave. We need to cut our delay time in half, because the shorter the delay time, the shorter the period of the fundamental wave that we're getting out of that. So that will bring us up an octave. And the way the waveguide delay is implemented internally in its own code is designed to do that math to convert this volt per octave signal into how short or long do I need to make the delay line relative to sort of my nominal state of 0 volts. Hopefully that answers the question. That's kind of how it works. The code example that we went through, which I can also make available for download later, does that math, but in based on just sort of internal pitches, just going up an octave based on some code. It's not taking external input. This module is doing basically that same math relative to the standards of volt per octave for VCV rack in order to derive how long the delay line needs to be to get the pitch we want. But that is also subject to what's in the feedback loop, because that adds additional samples of delay in our feedback loop. And then that's what this adjustment control is for, to sort of compensate for however much stuff we put in there.
What happens if we do not use noise, but any source of sound?
Yeah, it's a good question. Can I maybe patch something together to do this? So let's try like an oscillator. It's a little more interesting if you have percussive sounds and things with, a lot of energy, a broadband energy, and a lot of maybe transients. You can put like a drum beat through here. That would sound really cool. It sounds like a resonator. If you're familiar with like resonator type effects, that's kind of what it ends up sounding like. So let's replace the noise input here with, say, I don't know, something like a sawtooth with a lot of harmonics. So you can hear that our sawtooth pitch is still there. It sounds really cool. It's like basically the physical analogy would be like if you had a transducer, so a little, basically a speaker, but designed to mechanically vibrate another physical object. You put sound through a transducer and put it right on the string of your guitar, you would get a similar sound. And the resulting sound is going to depend on what frequencies are in the VCO, or what frequencies you're putting in to the system. So if we make this really high, we hear it a little bit at the very beginning, that very high frequency, but quickly goes away. What we're actually hearing resonate the system in this case is just the shape of the envelope mostly, because the shape of the envelope is also imparting its own spectrum onto the sound. So if we make this envelope really short or long, doesn't really matter much. It's sort of just imparting a little bit of overall energy into the system, but the frequency present in that sawtooth is going to influence what we hear. It's a great question.
Yeah, beautiful. It actually sounds it sounds really interesting.
Yeah.
Maybe a personal question: why did you not add an input on Audrey 2?
So, yeah, it's a great question. Audrey 2, you can add an input. So for those of you who aren't familiar, Audrey 2 is a feedback distortion, crazy swelling drone synth thing built on the Simple platform on a Daisy Seed. At its heart, it actually has a carplus-strung, a very, very, very simple carplus-strung resonator, much like the first example we looked at. But it actually is another outer feedback loop through a reverb, through some distortion to sort of simulate like air gap feedback to like electric guitar strings. Your amplifier is vibrating the air, and that air is vibrating your string, but that time that it takes to do that is much longer than the actual string delay time in its own internal vibrations. So if you can create crazy systems by doing stuff like this. An input to Audrey 2 does sound pretty interesting, but what we actually lack in Audrey 2 is some of the finer like tuning of the parameters are really more for that outer feedback effect. We can change the pitch of the string, but we can't change its damping like, for example, like that's like damping. That's just how much of a static amount of attenuation we're applying to the overall feedback loop. You can change damping. Of course, you can map that to like velocity and stuff like that to get a lot of expression. You can't change some of that stuff in Audrey, and I found that you can absolutely add an input, but if you have high feedback settings, the input kind of just dies. If you want to use it as like a resonator with the low outer feedback settings, it sounds like a resonator, but you don't have as much control over the parameters of a resonator that maybe you want. But if you turn that outer feedback up and it gets crazy swelling sounds, you kind of just completely lose the input. The feedback just takes over. So it's really only interesting, in my opinion, if you're using it as a resonator, like without that outer feedback, which is kind of what makes Audrey what it is. And if you're using it that way, you kind of don't have all the necessary granular control that you might want if you're using it that way. So it just felt like it's kind of doesn't want to be that right now. It could be that with more controls and whatever, but it kind of doesn't really want to be that. It wants to be this out of control feedback system where the input signal just gets lost.
Yeah, that's a very interesting design decision, because it actually confines the instrument and makes it a bit more constrained, and like that's how you should actually play this. Cool. Yeah, okay, so do you guys have more questions? before, like, I don't know if we should actually continue. Like, do you want to?
Yeah, I think just given the time, maybe we won't go into the other code example, but I'll just mention what you can do, and then I wanted to show a couple other interesting things we can do with this VCD patch. The other code example, which of course, I can also make available online, is using code that was ported from immutable code. So from Rings and Platts both have kind of the same code that Emily wrote for a much more advanced version of the CarPlus physical modeled string. Adds a bunch of extensions, including things like curved bridge nonlinearity, which is kind of supposed to sound like a sitar, or like instruments that sort of like have a curved bridge. I'm not 100% sure how that works, to be honest. But also dispersion, which is like deliberately messing with the phases of different frequencies, so the phase delay of different frequencies in the feedback loop. And we can actually kind of hear what that sounds like. It's an all pass filter in the Rings code, but we can actually hear what that sounds like here. So it gets really inharmonic. It just sounds kind of, yeah, like that's because the different harmonics of energy that are building in our waveguide have different amounts of delay based on the all-pass filter. It's really messing with the phase delay or the phase response of the feedback system. So different harmonics end up getting different amounts out of tune from actually being harmonics. So the resulting sound is quite inharmonic. So like a ring modulator or something almost. That is actually what the structure control on Rings, for example, affects that. The way Emily did it is a much more extreme all pass example. It can get really inharmonic, just sound totally outlandish, not like a string anymore, but like some crazy inharmonic out of tune physical system. That's all just done by putting basically an all pass filter in the feedback loop so that each harmonic has a slightly different delay based on the phase response of the all pass filter, and we get crazy sounds. So that's one thing the Rings code can do. All that is ported into Daisy SP, so you can actually use that on Daisy. The port has a few bugs, and I have been meaning to actually write bug reports for these, but it doesn't compensate for delay correctly if you like change the damping. The original code absolutely does. You can, increase the damping. So in other words, kind of like that. It's like increase the damping amount on the string so that it's like a muted sound, but we can hear that getting out of tune here. You can hear it going flat. The Rings code doesn't do that at all. The code that's ported from Rings into Daisy SP actually does go out of tune. It's not properly compensating for that. I think it's because they're using a slightly different filter in the feedback loop, but not, I don't know. I don't know exactly why, but it's not perfect. But it does sound similar to what you'd hear from Rings or Platts. So we can actually use that in Daisy code and create instruments based on a much more advanced version of a plucked string model.
Cool. How would you approach, like, if we're going the approach of transducer driven string? How would you approach this to design an instrument that is really trying to push the boundaries of this kind of sound?
In like a digital sense, or like if I were doing this on a real guitar? Okay, yeah. I mean, really, you can kind of do a lot of stuff. Like the excitation. So what you're putting into the system, the sound that is basically going through the transducer, the amplitude of that will affect sort of the loudness of the resulting sound. So you can play with the gain. You can filter that signal before it goes in. I was showing kind of these examples where you can filter this. You can also do all sorts of stuff. You can make it very resonant. So then that changes the sound a lot. Kind of whatever color you want to put on the original signal before it goes through the feedback system is kind of the excitation modeling. You can do so many things. I would definitely recommend crazy filter types. Things like that tend to have a pretty pronounced effect. What I didn't show here, this is actually if you wanted to emulate maybe a more realistic guitar string, you can use a comb filter. So you hear that higher harmonic changing a little bit. That's actually really, really similar to what happens when you pluck a string in different places. So, very close to the bridge, you get kind of this tinny high sound. Very close to the middle of the string, you get like a hollow sound. That all has to do with where the energy is sort of input into the system and what resulting cancellation effect that has on the energy that builds up in the string. You can sort of emulate that with a comb filter. So this is actually really should be a feed forward comb filter. This is a feedback comb filter with positive feedback, but it has a similar effect. It just sort of amplifies exact harmonics of the noise. So equal harmonic spacing, we're amplifying that in the noise before it goes into the system. And that has kind of a similar effect to like where you're plucking on the string. In this case, the frequency of that comb filter is directly proportional to the volt per octave signal. So that keeps that harmonic relationship the same no matter what note is going to be resonated in the waveguide delay. But yeah, I would definitely recommend filters like on the sound before it goes into the system. Once it's in the system, you can do all sorts of crazy things. The overall like amplification of the signal. You can even do feedback. It can get out of control. As with any feedback, I would definitely recommend being careful. Stick a limiter in there. Do something to protect yourself. But like, if we turn the gain up a little bit, that feeds back. So that's kind of how Audrey works, but on a much larger scale of feedback. So you can add feedback in your delay line. Definitely keep it really small so that you're not like blowing it out super fast. You can add really anything that's going to color the sound. Filters are kind of the obvious approach. But yeah, hopefully that is helpful in explorations of that technique.
Yeah, I'll combine a couple of questions here. Like when we're looking at this simplification of carpal strung, so Omri and Matthew also from Galax asked earlier about different instruments that are using this technique and really extending on it. And maybe in particular, I would love to hear if there are any specific instruments, maybe VST plugins, that are really exceptional in the way that they play with this, and they're really creative in that sense. Do you have any examples of?
Yeah, I mean, there are several examples that go beyond, like carpal strung is a very simplified version of the general realm of waveguide physical modeling. So anything that's sort of like energy resonating in a physical system of a certain length with certain reflections, along that length. That could be like everything from hitting like a metal plate to a drum head. Drum heads tend to be very inharmonic in that sense, but still very similar underlying physical principles. It's a waveguide of a tense membrane that's vibrating and reflecting off the edges in really complex ways. Hitting a tube. So I mean, mutable instruments, rings is like the classic, and elements, of course, it takes it a little further with all sorts of excitation modes. The classic sort of like really popular digital waveguide physical modeling tool. So rings can do all sorts of stuff. Like I said, it has a bunch of extensions, some of which were inspired by Jaffe Smith. Julius Smith, by the way, has a very math heavy but free and very available book online called he's got virtual musical instruments and physical audio signal processing. So he's got all these resources online. It tends to be very math heavy, but kind of is considered sort of the technical Bible for studying this stuff, I think, on a really fundamental level. So he developed a bunch of extensions for carpal strung soon after the original algorithm came out in the 80s. And rings, and really every modern version kind of uses some of those, better filtering, delay compensation so the tuning is correct, pick position emulation, which I kind of demonstrated here, additional sort of dynamics filtering. You can also apply like damping. Like let's say, if I let go of the key, maybe I want the sound to die out. This patch doesn't do that. But what I could do is when I let go of the key, actually reduce the feedback amount. So like, something like that. So reduce the scaling of the feedback in our loop. That way it basically just dies out really quick. It's like, immediately stopping the sound. Not quite immediately. It's not like a hard cutoff, but if you put your hand on a string, it dies out really fast. So that's one way you can emulate that. all those things. And of course, Rings takes it a million different directions with crazy enharmonic modes and all sorts of stuff. So Rings is a great example. Obviously, there are emulations of Rings and Plats in here in VCV Rack that you can use to play with that, even if you don't have a hardware system. Physical, like actual software instruments. I mean, the only ones I'm really familiar with are Ableton. For a long time has had a couple of physical model instruments. I don't remember what they're called, but Applied Acoustic Systems, AAS, developed the DSP for that. They also developed the DSP for IntelliGel's PLUCK module, which is a physical modeling percussion module that can do string sounds and all sorts of other stuff too. So those are good ones to play with. Like if you have Ableton, there are some instruments in there. As far as like VSTs or third-party free software options, I don't really know too many aside from what's in VCV Rack and what's in Ableton.
There's actually an interesting follow-up on this. So normally when we talk about physical modeling, you always have this exciter and the material. Like what's the name of the other?
Resonator.
Resonator, right. So exciter and resonator.
Mm-hmm.
When we look at this patch that you created here in VCV, because I'm assuming that these are basically translated from the code into something that's a bit more tangible for us to understand when we design the sound.
Yeah.
What is the exciter here? That's basically the noise?
Yeah, it's the burst of noise that we put through the delay line is the exciter. So the exciter could be any arbitrary signal. It could be, in the transducer emulation case, it could be anything. Samples, whatever.
So in the exciter, like I could make the exciter harder or softer, more like metal, more like wood, or like plastic.
Yeah, and there are some really advanced, physics-derived techniques for doing that, but really you can just play with filters and envelopes. So, resonant filter on the noise, this is still just noise. It's just going through a resonant filter, a resonant low pass. Obviously changes the sound a lot when the resonance is up. The length of the envelope, so you can make this a longer attack and decay. You start hearing the noise if it's too long, because it outlives the delay line. But yeah, that's kind of how you would do the exciter. And another cool thing you can do, which actually I've patched up here, I've got the envelope going through a delay, which right now is mixed out. But if we mix this in, let me turn that back up a little bit. We can actually get like kind of a hammered dulcimer, maybe something like that.
Beautiful. Yeah.
Like reflections of the.
Almost like hitting with a stick on the string and letting it.
Yeah, exactly.
Like bounce. That's beautiful.
Yep.
Great. You guys have any further questions? Because before we wrap things up, feel free to ask them now. Nick, did you have anything else that you want to share with us today?
No, I mean, no, this has been great. It's been really fun just playing around and listening to the feedback of what people want to hear more about. And thanks for the opportunity. I will work on getting all this stuff available online for you to play with. And if you have the Simple Kit or, Daisy Seed in general, any of the Daisy platforms, you can start playing with this stuff in Daisy. The Car Plus String, I think, is what the class is called in Daisy DSP, or String Voice, which has the exciter built into it based on the Platts code. And I think there are some examples in the library as well that exercise that that were written by Electrosmith. So yeah, really love this technique, and thanks for the opportunity to talk about it.
Yeah, absolutely. I mean, I feel like everybody here feels the same, that we're really fortunate to have you on Discord, and now that we're actually starting these sessions, this is absolutely fantastic. I know I learned a lot. I see a lot of people very happy on the chat as well. Someone said that it's this VCV tutorial doesn't feel right without Omri saying "oh yes," so I'm expecting Omri to say "oh yes" in the chat here. Or opala. Hopla. Yeah, no, this is great. Thanks so much, everyone, for joining. This is since we started this with Vlad, this feels even more like a community than what we have on Discord. So we're going to push and make more of these. The next one is going to be next Saturday with Vlad, and we're going to. I'm not sure what the topic is going to be about, but we've already set up a Google Calendar that you'll be able to sign up for. So if you are on the newsletter or on Discord, you're going to get a notification about this. You'll be able to just sign up to a Google Calendar. And in the Google Calendar, you'll see all the lessons that are coming up, so you could really not miss any of them. I think this is a great opportunity for all of us to learn and hopefully make more instruments, more wild ideas coming to life. That's basically the vision of this academy. And yeah, thanks so much for being here.
Thank you.
Cool. Yeah, we'll see you guys on Discord. Bye.